Hello, everyone. It's super nice of you guys to join us. Um, my name is Mali. I work on data infrastructure, and I've been at HubSpot for 6+ years. Now, throughout this talk, there is a Slack channel that you can join, Epic Week 2025 Billion Rows, which will have links to these slides and as well as code samples. But today, what I want to talk about is the 1 billion row challenge. So this is a challenge where you have a file that has 1 billion temperature values. And each one of the rows in this file is the name of a city, semicolon, and then a temperature. Got 1 billion of these. It's about 14 gigs. And you're supposed to write a Java program that processes through these as fast as possible, right? And returns a result like this, where you get a name of the city, and then you have the minimum value seen, the mean value overall, and the max value for each one of those cities one by one. So it seems deceptively simple, but you're supposed to do it really, really fast. Um, so let's set up some speed expectations, right? Like what's our ballpark, upper and lower bounds, etc. So the first thing that I did is I ran this benchmarking program called FIO, where basically what I wanted to see was like literally just reading the file as fast as possible, right? Like how long would it take? Well, it took around 600 milliseconds, so a little over half a second. So that's basically our absolute lowest bound that we can't possibly beat, right? And then another sort of place to get our ballpark is that, this question might seem familiar to you if you did the HubSpot Reliability Regatta or the Grow Day Regatta competitions. It was one of the questions in there. It wasn't specifically named as such. But anyway, the best result that we got from there was around 14 minutes of execution time. And then another way to get a ballpark is, okay, let's use some sort of like out of the box computation engine, right? Something like, you could use something like Spark. I used Polars, which is basically a Python Rust optimized data frame processing streaming thingy. And I got around 33 seconds. Um, and then finally, there's a sample code in the repository, right? And it takes around 3 minutes and 11 seconds, right? It's around 85 lines of fairly straightforward Java code, right? Could be written by any one of us, mostly fairly idiomatic. But if you look at the winning result, it's actually only 1.45 seconds, right? Not minutes, seconds. So that's 130 times faster than this baseline implementation. And that's about processing about 9 gigs of data per second, right? And that's around 430 lines of extremely, truly, really dense code that's like full of bitwise hacks and magic numbers and written by people who are really, really experts in this sort of stuff. And the code just kind of looks like this, which kind of reminds me a little bit of like this. Um, and so the question that I want to pose today to all of us is basically like, how fast can we go without necessarily being gross? Um, so what we've learned so far is that we should be somewhere between like the lower bound of 0.65 seconds and the upper bound of 191, hopefully close to the 1.5 seconds that was like the world record winning champion. Um, Okay, so I want to take you through the baseline implementation and what that looks like. So here are the data structures that are used in here. So first, you have this like measurement class that sort of determines each line in the measurement file, right? So you've got like a string that's like the station name or the city name, and then you got this like double value that's like a value, right? So like London, comma 33.0. And then you have this result row, which is for the output, where basically, okay, if you have a city, you want to save like the minimum, the mean, the maximum, and it does some like nice rounding for us and puts slashes in between stuff, and it's mostly cosmetic. And then we have this measurement aggregator thing, which is like uh, fairly important to the core idea, where basically we want to keep these like running sums of things. So if there's a minimum, we want to keep a what's the current minimum that we've seen so far, what's the current maximum, what's the sum, so add all the numbers, and then what's the count. And we do this for each city that we have. So if you look at the main loop of the code, the way that it looks like is, okay, so you get the file, you pipe it into files.lines, right? And that gives you a stream of like lines that look a little bit like this, right? And then you split it by the semicolon. So you now got London and 33, stick it into a measurement object, right? And then you just do collect, group by the name of the station, and boom, you're done. Now there is this like collector thingy over here. And that does basically the measurement aggregation thing that I was telling you earlier, right? So if we have a measurement aggregator and we're going to add a new value, well, if that's the smallest value that we've seen so far, then we should take that one. Otherwise, we should keep our current value, right? And for the sum, we should keep adding. And for the count, we should keep incrementing the counter, et cetera, et cetera. So um, so the first thing that came to my mind is, okay, my laptop has like 10 CPU cores and I want to use all of them to the max. So it turns out this is actually really easy to do if you're using Java streams, right? You just stick a dot parallel in here and then boom, well, we're now down to like 60 seconds, which is like a 3x speed up. So this is kind of incredible, right? Like Java streams are awesome, awesome value. If you're writing your code like this anyway, just sticking in a dot parallel seems like there's never any reason not to do it personally. That's my hot take on this. Um, but okay, so we got the easy win. So now what? Well, I want to talk a little bit about flame graphs, right? So what a flame graph is basically a chart that shows you your program execution and it shows you what takes time in that execution. So at the bottom, we have this sort of bar called all, which is basically like your whole program. And then you got these like increasingly smaller bars that are like the functions that we're calling. So in here, I have an unnecessarily complex temperature processing function. And the reason that that takes a bunch of time is that it calls a waste time on purpose function. And the reason that that takes time is that there's like a is prime the slow way function in here, right? So you see kind of like in one glance, what's taking the most amount of time? Well, this function is taking around 80% of my time, so maybe I should be optimizing that. So now let's look at, well, yeah. Let's look at what the flame graph for our baseline parallel implementation looks like. So one big thing that we see here is like string dot split, right? So that's basically taking our London semicolon 12.4 and turning into London 12.4 and doing that 1 billion times. So that takes a lot of time, right? And similarly, there's parse double here. So basically 12.4, the string turned into 12.4, the number. And again, we're doing that 1 billion times over and over and over again. So the question is, these are like JVM internal functions, right? So can we do better than the JVM? Well, let's give it a shot. So if you look at string.split, you'll see that it actually takes a regular expression. And maybe it's doing some fairly complicated like regular expression BS, right? And maybe we could come up with something simpler. So instead of splitting by semicolon, what we can say is, okay, give me the index of the semicolon, right? Let's find where the semicolon is. And then let's say, okay, everything from 0 to the semicolon is the name of the city. And then everything from the semicolon +1 on is the temperature till the end of the line. Okay, so let's do that. And when I run it, it's like womp womp. Well, you get, an improvement, but it's like within the margin of error. It's not really like a great improvement. So fine. Okay. And if we actually if we expand this flame graphs, you can do that. You can see what those are calling. You can kind of see that it was actually doing string dot substring and it was doing index of. So it was doing pretty much exactly what we were doing already. It was already fairly optimized. Okay, what about like double dot parse double, right? Like parsing these strings into like numbers a billion times. It does this like read Java format string thing internally that looks like maybe it's complicated and maybe we could do better. Um, so we can kind of implement this method where it's, let's say we got 37.2. We can kind of like loop through every single digit, right? We can say, okay, we got the 3. So it's like 3 times 10 is 30. And then 7 times 1 is 37. And then 2 times 1 over 10, et cetera, et cetera. So we got this like parse double function that does pretty much what I explained. And, womp womp, we get like another improvement that's like a little bit better, but it's like, it's not crazy, right? It's not super helpful. So what we kind of learned here is that it's hard to beat the JVM with just micro optimizations. So then time to switch gears, right? If we can't do micro optimizations, then what are we going to do? Well, if we go back to the original code, we'll see that this files.line stuff is actually not happening in parallel, right? All the stuff afterwards, the collecting and the grouping by and all that stuff is happening in parallel, but reading the file is actually a bottleneck. So this is what's called an embarrassingly parallel problem, which is basically a problem where you could literally take the problem space that you have, and if you have, I don't know, like 10 CPU cores, just divide it into 10, and then do the same thing in every single chunk of the problem, and then just kind of like combine them at the very end. And so to be able to do that, we have this like sort of calculate chunk boundaries thing that figures out like where your chunks are, right? There's some fiddly bits here involved with like, okay, maybe you don't land exactly on the new line, and so you got to like go back and forth a little bit. But then we have this main function called parse chunk with IO, where we give it a chunk and it does, the whole thing. And then at the end, we like merge everything together. And then if you look at this part chunk with IO, what it does is it does this like read fully function where it basically reads the entire chunk into memory all in one go, right? And then it does the usual stuff that we mentioned, right? Find the semicolon, extract the station name, find the new line, parse the temperature, and then aggregate stuff. So boom, suddenly this gives us a lot more of an improvement. So we're now down to like 15 seconds, which is pretty darn good. So what we learned here is that like architectural and algorithmic changes can often result in big performance wins in a way that micro optimizations might not. So this is a good place to look at first. But okay, so we run the profiler again, and suddenly doubles haunt us again, right? Here we see parse double, right? And then Java string dot init. So we're allocating a string and passing it into parse double. Um, and it's taking actually a lot larger of an area than previously it used to. So can we do better, right? And this is where the parse double is happening, where we get like, okay, we go through a char character array, we create a string only to like dump it into parse double, and then we throw that string away. It's like a temporary thing. So can we avoid that is the question. And which we had tried parse double before, so why do we think it might work this time? Well, in the single thread implementation, the IO stuff was taking like 80% of our time, and the parsing was only 14% of our time, right? So this little area improving that wasn't giving us a big gain. But now that we improve the IO, suddenly the parsing is the big bottleneck, right? And so now any improvement in the larger area is now going to result in something significant. So this is called Amdahl's law, where basically if there's heavy traffic on the way to work, right, making breakfast faster doesn't really gonna help, right? But taking a helicopter to work, right, does. So the context of the optimization and like where you're applying the optimization really actually matters, right? You should be applying optimizations on the current bottleneck, and that will be creating new bottlenecks that are then worth fixing. Okay, so we have parse temperature is double, and now instead of passing in a string, we pass in a byte buffer, and we like work on that byte buffer, no problem. And we're down to like 8.7 seconds, so that's another pretty great win for us. So, and what we learned from this is basically doing simple things 1 billion times can get really expensive, right? Especially if the 1 billion times is the thing that's taking the most amount of time. Okay, so now let's see if we can do the same idea in other places, right? There's also another place that we allocate these extra strings, right? And that's when we're extracting the station name from and then we're sticking that station name into this chunk results.compute of absent, where basically we're getting the measurement aggregator for the city. So we're like looking it up in the hash map, right? So what do we do about that? Well, one idea is that we can get rid of the other string allocation in here, right? So um, we can say that a station key, instead of being a string, is an array of bytes, right? We create the station key wrapper for it to make it all nice. And boom, that gets us down to like 7.3 seconds. So far, so good. What else? What are we doing more than 1 billion times? Well, we're like looping through every single digit of every single number over and over. But if you look at it more closely, there's only two possible formats, right? It's either like one number x dot x, which is one number dot one number, or xx dot x, which is like, two numbers dot one number. So instead of writing a for loop, I can just have an if statement and I can say, well, if the dot is here, then it's got to be the x dot x format. So then we'll take the 0 thing and multiply that by 1 and sort of like do this multiplication algorithm directly, right? And similarly, if the dot is in the next spot, then we can kind of like immediately multiply these things without having to resort to a loop. Um, So this is the code that does that. And boom, that takes us down to 4.9 seconds. So this is called loop unrolling, right? Loops that are predictable, right, that have predictable paths can be unrolled. And predictable, this is why predictable formats are good, right? If you have a file format where things are fixed length or you previously know the length of things so you don't have to scan through the file, like stuff like this allows you to do optimizations when you're reading the file. Okay, so then what's sort of left? Well, parse double, we kind of like improved that one. String allocations, we kind of like got rid of a bunch of those. Um, so what about this like hash map compute of absence? Like what are we going to do about that? Well, the question is, okay, so can we go even simpler and even dumber than Java hash maps? Well, let's take a look at how hash maps work, right? So you have a bunch of keys, let's say Lisa Smith, you run a hash function, and that gives you a number that maps to these buckets that you have, right? And if you get one, Lisa Smith is like right here, okay. And there's like a slightly more complicated case, right, where you have John Smith and Sandra D, and it turns out they hash to the same value. So what do we do then? Well, the Java implementation does some fairly complicated things, but instead of doing complicated things, what we can do is basically just say, okay, well, this area for John Smith is full, we'll just plop Sandra D to the next available spot, right? And then here comes Ted Baker, and Sandra D took that spot. Well, we'll just plop Ted Baker to the next available spot, right? So plop it in the next free spot seems like a really stupid strategy, but it's actually called linear probing, and it's a real thing. Um, and another simplification that we can do is we can say, okay, well, these buckets don't need to be like expanded and resized. We'll just make like a big one, and it'll be big enough for the whole file. So, all right. So our hash map kind of looks like this. We have like our buckets over here. We have this get or create function, right? We have this compute hash, and then we're like looking stuff up in a while loop. We're basically seeing, okay, is this our station? If it's equal, then return the value. Otherwise, add one and look at the next place. And then if you can't find anything, then just create a new city and measurement aggregator in there. So that's pretty much it. And that takes us all the way down to 4 seconds. So, so the learning here is that when the use case is heavily constrained, we can often beat the standard, right? Things that are in standard libraries and stuff, right? They're optimized to be able to serve every possible use case. But if you have a very specific use case, right, this is a very HubSpot-y way of thinking of things. So in a lot of cases in HubSpot, we won't reach for the off-the-shelf solution. We'll try to build it internally ourselves because we say, okay, well, this thing has 8 zillion features, but we only need these 3 features. And if we only build those 3 features, then, well, maybe we can get something that's super tightly integrated into the rest of HubSpot. So, if the use case is constrained, maybe it's worth building it yourself. Okay, so can we avoid copying anything at all ever, right? So you have this like read fully function that reads the whole chunk into memory, right? And this is sort of like loading up this massive segment of a file means that like under the hood, what's going on is the operating system has to read the file for us and copy it into our process's memory, right? And here's something related, which is like this new array, which is allocating that big byte array that that chunk has to go into. So we want to like eliminate these things. Well, turns out there's a method called memory mapping. So let's say you have a file with a bunch of data in it. You can kind of like create this thing called a memory map that looks like a byte array, right? But what it's actually doing is it's like lazy loading stuff. And so the operating system doesn't have to copy anything. So what you can do is instead of doing like byte array square bracket like my index, you can just do file segment dot get my index and you get a byte back. So it works. It's pretty easy to work with, but under the hood, instead of loading everything, it'll load like just the chunks of the file that you're reading, and it'll do some smart stuff like prefetching, the next stuff. So because it thinks that you might read the next stuff as well. But the point is that we can avoid copying this whole thing into memory all in one go. Um, so doing that gets us down to 3.4 seconds, which is also pretty darn good. Um, okay, so we're doing pretty well. So then the question is, can we get even more parallel, right? So now we've like optimized the heck out of almost everything. So now we're like seeing, okay, get new line position and get semicolon position, right? We're spending way too much time getting the position of semicolons and new lines, and we're doing this again in a loop one byte at a time. Well, so what I want to show you here is an analogy where basically this is like a hole punch where you take a piece of paper and you can just go ka-chunk and make little holes in it, right? But punching holes one by one takes forever. So someone invented this like sort of multiple hole punch where you can put your sheet of paper in there and just hit it in one go and you get ka-chunk and you get like three holes all in once. Um, so very similarly, in computer science, there's a thing called SIMD, which stands for single instruction, multiple data, right? Instead of doing like addition one, addition two, addition three, addition four, right? You can kind of have this one single instruction that adds all four things all in one go, and you get a parallelism of 4x. So how does this even help us at all? Well, what we can do is instead of using the plus operation, we can use the and operation. And so here's a line of our data. We got like a city name, semicolon, minus 11.2, and a new line. And we can and that with a series of semicolons. And so wherever we end up with a 1 is the position of where the semicolon is in the original place. But we did this now, we have like 16 semicolons, so we did this at 16x parallelism. So Java has a vector API that does this cleanly. So instead of doing really gross bit shifting stuff, you can say, okay, here's my semicolon vector. It's just literally a string of semicolons. And then I want to compare my chunk to that, and I want to compare it with equals, and just give me the first thing, the first one in there, right? And that says, okay, the seventh value is the first where the semicolon is. And doing that, we're all the way down to 3 seconds. Okay, so we're like running out of stuff here, but there's this compute hash function here, and maybe we're just spending too much time computing hashes. Well, hash functions seem like they're this like sort of super duper magical thing that no one really knows about and understands. But actually, all that a hash function is just something that creates enough variance, right? All I want is if I put the hash function on key value A versus key value B, it should end up in like slightly different places. So then what got me thinking was, okay, well, what determines like the two places are different? Well, we can compare like instead of comparing the whole string, we can say, okay, let's compare just the first character and just the last character. But there's also like a bunch of things that have the first and last character in there. So let's throw in the length as well and just kind of like make something up, right? So I call this bullshit hash and I completely made it up, but it works just fine. And I will show you in a second how it works. But there's one more thing that we can do with a profiler, which is basically make this sort of like thread chart where each one of these is our execution threads, right? And we can kind of see the work being done over the course of the entire program. And if you look over here, right there, you can see that there's like this red chunk at the end where some of the threads finish faster than the others, and they just kind of like sit idle, right? So what can we do? Well, we can use this technique called work stealing, which is basically like once those threads are done working on things and they're sitting idle, they can just we can create a queue of work and they can just pick up more work. So instead of predetermining this thread gets this thread gets this, we have this like big queue of work that's like being served, and each thread can like grab stuff if it runs out. So, and then we combine that with like sort of a lot smaller chunks to fill those like small gaps, and suddenly we have basically maximized parallelism. So now we're down to 2.8 seconds. Okay, so this is pretty darn fast, right? The winning entry was 1.5 seconds, and we're at 2.8, so we're like better than half. So the question is like, can we go cleaner? Well, I tried to create this like enterprise version of this where I have like this config builder that has like a chunking strategy and a parallelism level, and it has a processing pipeline that you stick that config into. And I have this chunk processor interface and a vector API chunk processor. And we've got different execution strategies, different result collectors. And you'd think that this might have a lot of overhead. But if you look at this thing, as long as the architecture remains the same, we're still at approximately 2.8 seconds. Like it's not really adding a lot of overhead. Now, in the first version, I avoided in the hot loop, like sort of having these like replaceable components. But even if I throw those in there, so let's say I have a byte scanner that helps me look up for semicolons and new lines, and I have a temperature parser that helps me parse temperatures, and those are also swappable. I'm still only up to like 2.9 seconds. We're still sub 3 seconds, which is pretty darn good. So the penalty for decent encapsulation isn't really that high, like especially if you avoid the on-hook pass. But even if you don't, like it's really, really worth it. So conclusions. Number one, profile guided optimization is the way to go, right? Don't throw stuff at the wall and see what sticks, right? Use the profiler, see what there is to improve, improve it, confirm that it actually got improved, and then move on to the next thing. Second, is LLMs can automate the testing out of theories, right? Whenever you're working on a big performance problem like this, you have a zillion different theories, and exploring every single one can get complicated, right? But what I've been doing, right, there's actually 30 or 40 different variations that I've shown you in this talk. Some of them I haven't shown you. And so what I've done is mostly said, hey, Claude, like I want to use the vector API to parse this thing and use it this way. You want to go do that? Yeah, go do that. And then look at the result, make sure it did the right thing. But then that's a lot faster and a lot cheaper than trying to implement all those optimizations myself. So the key here is that today, like just knowing a concept means that you can sort of apply it somewhat, right? So this should encourage you to learn a lot of different techniques and concepts like work stealing, memory mapping, SIMD, and all these things that we talked about in this talk, right? Just understand a little bit about what they are and how they're used, and suddenly you too can be dangerous. Um, okay, and then architectural improvements generally beat out micro optimizations unless you're squeezing the very, very last bit off. Um, and finally, encapsulating your optimizations and wrapping them up into like nice classes and interfaces and stuff is generally worth it, right? You take a small performance hit, but generally you can encapsulate in a way that doesn't really affect stuff too much. And that's pretty much it. Um, Please, yeah, like if you have any questions, we're like pretty much out of time exactly. But you can go to the Epic Week 2025 Bill and Rose channel, and I'll be happy to answer them over there. Thank you so much.